Welcome back to Quantum Lab.
This just arrived. I think it's important.
Oh, thank you. I'll open it immediately. It is important.
Good morning, Mr. Stute. Your mission, should you choose to accept it, is to build a custom device that will reveal information contained in a Young's double-slit experiment laser dot. This message will self-destruct in 5 seconds.
Well, let's try that again. Welcome back to Quantum Lab. I am JosephStute. Some of the experiments I design and build seem like being part of the Mission Impossible team. Here's an example. Using my imagination, I saw the laser dot as similar to microdots used in spy stories for passing secret information. My laser dot is just like a microdot. It is loaded with valuable information. I will set up my laser microdot reader on my favorite workspace, the Quantum Lab Break Room Pool Table. A laser with a dot about 3 millimeters in diameter is aimed at a piece of flat wire 0.2 by 2 millimeters purchased from Amazon. The screen is a half sheet of glossy photographic paper. I placed it about 20 centimeters from the laser. The slide is made by cutting 2 L-shaped pieces from an index card. Tape them together, leaving a 4 millimeter slit in the center. Tape on the flat wire, and you are ready to begin. When the flat wire is centered in the middle of the beam, the dot looks like this. I have seen this dot hundreds of times. Very boring. Only recently started to wonder, could there be more to it? One of my favorite tricks will give us a look inside. Here is what happens when I give the screen a twist. Twisting the screen is like using a magnifying lens. The photons spread out. Hey, what is this? Not boring at all. As you can see, there is a mini light-dark pattern. Does not look anything like the pattern we see at 2 meters. I thought looking at the pattern created by twisting the screen would be the end of the story. Like many experiments, answering one question simply created another. The next chapter in the story is, how does the pattern observed at 8 centimeters turn into the one at 2 meters? How does the dot transform into the familiar pattern? To answer that question, I went into the Quantum Lab machine shop and built a camera transport system, or simply as I like to call it, the sled, because it has smooth plastic skids on the bottom to help it slide across the pool table. For construction details, check jsquantumlab.com. This experiment is called, no surprise, Stute's sled run experiment. Building the sled to transport the screen and camera was well worth the trouble. Now that you have the general idea, let's go to lights out. The sled run experiment starts with the screen as close to the flat wire separator as possible, about 7 centimeters. These 2 light-dark patterns are called diffraction patterns. A few light-dark spots, separated by large space with very little light. That will change, because the pattern constantly changes as the sled moves away from the laser. The sled is now 20 centimeters from the laser. Out of nowhere, small spots appear in the middle and at the edges of the pattern. These emerging patterns are called fringe patterns. To save time, the sled has been moved to the 1 meter mark. Watch as the 2 patterns change shape and spread out as they merge. The sled has moved to the 2-meter mark and the end of the track. From laser dot to dashes, the two patterns are constantly changing. How my edge demonstration's laser dot turns into a light-dark pattern might be confusing. The laser dot is composed of light and dark spots we cannot see because they are small and close together. Twisting the screen spreads the light-dark spots, similar to spreading cards on a table. Light is not as simple as most sources of information mislead you to think. The presence of two distinct patterns suggests there is an alternative to wave interference theory. Two patterns indicate light reflecting off the double-slit edges. I know that sounds ridiculous, but watch this experiment and tell me what you think in the comments below. The laser is aimed at two razor blades approximately 1.5 millimeters apart. The separator is a round wire about 0.1 millimeters in diameter. Here is the expected pattern, or more correctly, two patterns. Look what happens when I give the separator a little twist. The result looks like this. The diagonal pattern is created by light reflecting off of the twisted separator. The horizontal pattern is light reflecting off the outer edges of the slits. This experimental result reminds me of the opening to my first video, where aiming a laser at a single slit produced two patterns. Giving the slit a twist caused the second pattern to move, just like twisting the separator in this experiment. If you'd like to see the entire video, click the link shown here. Both experimental results fit perfectly with the formula for reflection, which is changing the angle of incidence changes the angle of reflectance. I do not see how wave theory can explain two patterns. Can you? Please comment below. Otherwise, like and subscribe if you want to see more videos debunking Young's wave theory.